8, Sandra makes repeated independent attempts to hit a target. On each attempt, the probability that she succeeds is 0.1. Ooh! What's this?
Maths.
Good. Josh. This is a geometric distribution, isn't it? Because the probability remains constant. It's independent attempts. Find the probability that the first time she succeeds is on her 5th attempt. So let's just set this up. This is we've got a geometric distribution, and the probability of success is 0.1. So the first time she succeeds is on her 5th attempt. That's the probability that x equals 5. Again, we can look in the formula booklet for this and find the formula there for these probabilities. That would be 4 failures followed by the final success, and that gives us 0.06. I think, to 3 significant figures. So there we go, that's quite a nice start. Part 2 says, find the probability that the first time she succeeds is after her 5th attempt. Well, what does that mean? If the first time she succeeds is after the 5th attempt, that's x being greater than 5. If that's going to happen, she must have 5 failures. If the first success is going to be after the 5th attempt, she has to have 5 failures. So that is 0.9 to the power of 5. That would be the condition for that happening, and that is 0.590, is it? I think. Again, 3 significant figures. Okay, that's quite a nice bit at the start of that question. You've got 4 marks in that. The second time she succeeds is before her 4th attempt. We've got to think about what that means is happening. Now, the second time she succeeds, that is before the 4th attempt. So that means in her first 3. So she could have succeeded on her first 2. It could be success followed by success. In which case, it doesn't matter what happens next. We don't need to consider what happens next, because that's succeeding before her 4th attempt. Or she could succeed and then fail and then succeed. That would satisfy it, because that would be a second success before the 4th attempt. Or she could fail and then get 2 consecutive successes. So those are the only 3 ways that it could happen. Notice it's quite important here that we don't consider what happens after that second success, because it could be either a success or failure. And it doesn't matter, all we need to know is that there's been 2 successes. So that one is 0.1 times 0.1. That one is 0.1 times 0.9 times 0.1. And that one would be 0.9 times 0.1 times 0.1. And if we add those 3 things together, it comes to 0.028. And that would be our answer to that. Okay. We'll talk in a moment about the fact that quite a few of you turned that into a binomial distribution question and came up with 0.027. And we'll talk about why that was incorrect. But the 0.027 is what you get if you also include the probability of that one then having a failure after it. But that's by no means part of what we're doing. It doesn't matter whether that was a failure or a success that came after that, and so that's why that probability wasn't quite right. Does that make sense? If we had F there, then that would be a simple binomial, wouldn't it? 3 trials and 2 of them being a success. But you need to know that it wasn't that. There's a slight difference. The next bit. Jill also makes attempts to hit the target. Each attempt of either Jill or Sandra is independent. Each time that Jill attempts, the probability that she succeeds is 0.2. So it's the same deal, but she's slightly more likely to succeed. Sandra and Jill take turns attempting to hit the target, with Sandra going first. It's important that we've got to think of these happening in sequence. Find the probability that the first person to hit the target is Sandra on her second attempt. Sandra goes first. So what happens there, in order for that to happen, is that Sandra has her first attempt and fails, then Jill fails, and then Sandra succeeds. That's what we want to happen there. So that is for part 2, part A. We've got Sandra fails, and then Jill fails, and then Sandra succeeds. And so that was 0.9 times 0.8 times 0.1, and that's the only way that we can tick the box of what we wanted to happen there, and that is 0.072. And then it gets a little bit more complicated. We now have the probability that the first person to hit the target is still Sandra, but this happens on her 10th attempt. So let's think what must have happened there. Remember, they're alternating. Sandra's going first. Her first success is on her 10th attempt. So that means she has 9 failures. And the probability of her failing, well, let's think, they're going Sandra, Jill, Sandra, and then Jill, and then Sandra, and then Jill, and so on. We could write down all of that, but we probably don't want to. If we think about what's going to happen, Sandra's going to fail 9 times. Jill needs to fail 9 times. And then eventually, Sandra has to succeed. And all of that has got to happen kind of in a linear way, one after the other. They've got to do this. And so as these are happening, it's like an enormous tree diagram. If you imagine all these branches going all the way along, you would multiply all the steps of the branches. So we've got to multiply all of these together. Of course, it doesn't matter what order we multiply, but we've got to make sure we've multiplied all of them. So we're going to end up doing Sandra's 9 failures. That's 0.9 to the 9. Jill's 9 failures, 0.8 to the 9, and Sandra's success. Sandra was the 0.1 succeeding. And if we multiply all that together, your calculator probably turns it into standard form. It's 0.0520. So 3 significant figures. And that would be the answer. Oh, yeah, and are you ready, Dan? And that's maths.